And welcome back. So today we actually get to start 4.1, which is going to be the antiderivative section, which a lot of fun. Y'all are in for a treat today. But before we get to that, let's go ahead and knock out the homework from last time. This is the optimization homework. So this was from 3.7, and we start off with number 16. And so we were given that the function was y is equal to x squared minus 2, and we want to know what point on that function was closest to 0, negative 1. Okay, so over here I'm going to draw a little quick sketch of what this looks like. So 1, 2, 1, 2, 1, 2, something like that. And so I'm going to have something that does, let's see, that's going to hit right there. So at negative 2, yeah, if x is 0, then y is negative 2. And where does it cross here? Let's see. So when y is 0, x is square root of 2, positive negative square root of 2. So that's about 1.4. So somewhere around here and somewhere around here. And so I get a parabola that does something like this. And it opens up a little bit better than what I have it drawn, but that's basically what we have. And our point is located right here. And it wants to know what the closest point or points are on the graph to this location right here at 0, negative 1. So this is going to be the distance formula again. So we've got our distance is equal to square root of, we're going to have x minus x1 squared plus y minus y1 squared. Okay, now let's apply the constraints. So the first constraint is going to be our point. So d is equal to square root of, we're going to have x minus, there's the x1, that's 0, squared plus y minus negative 1 quantity squared. So that's the first constraint. We've got the point down, but I need the second constraint so that I can find the distance between the two. So the second constraint is the actual function itself, y equals x squared minus 2. So I'm going to get x minus 0 squared plus, I'm going to have, instead of y, x squared minus 2, so this little piece right here is now going to be substituted in for this piece. And so I'm going to get x squared minus 2, and then this is minus negative 1, that's plus 1 quantity squared. So d is equal to square root of, this is going to give me x squared plus x squared minus 1 squared. Okay, so come over here, d is equal to square root of, we're going to have x squared plus x to the 4th minus 2x squared plus 1. That's what I get if I expand that out. X squared minus 1 times x squared minus 1 gives me this right here. So now I'm almost there. I can combine the x squared terms, so I'm going to reorder this as x to the 4th minus x squared plus 1. Whew. So this is our expression that has been constrained. Just for completeness sake, I probably should have said that. This is our min-max expression right here, and these two were our constraints. So just want to make sure I said that. I think I said that last video a few times. So what I want to do now is to find the minimum value in the system. The minimum value is going to be when I take the derivative, set equal to 0. But as we talked about in the last video, the minimum of the square root function occurs when the minimum of the piece inside the square root is found. That's probably extremely poor grammar. Let me try that again. I find the minimum for the root expression when I find the minimum of what's in the root. There, I like the way that says. So I'm going to kind of label this d2 is equal to x to the fourth minus x squared plus 1. So d2 prime is going to be 4x cubed minus 2x. All right, and we'll go over to the next page, clear this so that I don't get too crowded. So clear that. Eventually we'll be able to clear. So I had my d2 prime, I had that equal to 4x cubed minus 2x. And so now that I've got the derivative, I set it equal to 0, so I get 4x cubed minus 2x equals 0. I'm going to divide everything by 4x, so 4x leaves x squared minus 1/2 equals 0. Okay? So the solutions for this are when x equals 0 and x equals plus or minus root 1/2. Okay? Which is plus or minus 1 over root 2, which is plus or minus root 2 over 2. The reason I did that is I actually know that value sings to me because I know that root 2 over 2, root 2 is 1.4 something, divided by 2 is 0.7-ish. So I've got x equals 0 and x equals plus or minus 0.7-ish. Alrighty? Now, what I want is the points that are closest on the function to the point at 0, -1. Now, this is where it gets a little bit interesting because I have 3 solutions. I've got x equals 0 and x equals plus or minus root 2 over 2. So, are all of them correct? It turns out they're not. So, when you are solving for these optimization problems, sometimes you're going to wind up with values that are what are called extraneous solutions. And you may have seen extraneous solutions talked about in the college algebra or pre-calculus. Sometimes when you solve an equation, it turns out the solutions aren't actually real. And so we have these 3 solutions here. It turns out that they're not all minimums. They are given, some of them, I don't want to spoil it, some of them are the correct values, some aren't. So how do we test it? Well, the easiest way to test this is to test whether or not we have mins or maxes, okay? Because the ones that are the mins, so think about it this way, if I've got a distance function, so a distance function, and I take the derivative of that, so this thing prime, and then set it equal to 0, what I've got there is the slopes of the distance function. That tells me when they're horizontal, right? So I've got the places where the distance function has a horizontal slope. What I want, though, are the values that are minimums. That occurs when my distance function, which I'm going to abbreviate as f, and so this would be f prime equals 0. If f double prime is negative, so less than 0, it means I have something that is concave down. This is a max. If I have f double prime greater than 0, that means that it is concave up. And that means it is a min. So what I want to do is to take the derivative of the d prime over here and then plug in test values and see if I wind up with a value that is less than 0, which means that at that location it's actually a max. Hopefully you can hear the air quotes I'm making. And if it turns out to be greater than 0, that means that it is concave up, which means we have a min. So let's plug these values in. We've got to test x equals 0, x equals negative root 2 over 2, and x equals positive root 2 over 2. Okay, so those are the ones we need to test. So first off, this is going to be my f prime. So f prime of x is equal to 4x cubed minus 2x. So f double prime of x is just going to be the derivative of that, which is going to be 12x squared minus 2. Okay, so let's start plugging in these values. F double prime of 0 is going to be 0 minus 2, negative. That means it's negative, it's concave down, which means that we have a max. So x equals 0 is not one of the actual solutions. Let's try these though. F double prime of root 2 over 2. Well, and I can do plus or minus because I'm going to be squaring it. It's going to give me the same value regardless. But when I take root 2 over 2 and square it, I'm going to get 2 over 4, so 1/2, times 12 is 6, minus 2 is still positive. So since it's positive, that means that it is concave up, which means we have mins at those locations, which means that these are the actual shortest distances. So now that I've figured out that my values I want to look at are x equals plus or minus root 2 over 2, I can actually go find the point on the graph. So how do I find the point on the graph? Well, I need to look at my original function. F of x was equal to x squared minus 2. So f of root 2 over 2 is going to be, root 2 over 2 is again 2 over 4, 1/2 minus 2 is 3, negative 3/2. So what are my actual minimum distance points? Well, they occur at negative root 2 over 2, negative 3/2, and at positive root 2 over 2, negative 3/2. Those are the points on my graph that are closest to the point 0, 1. Now I'm going to pause this for a second and then show you Desmos to show that we actually got the right value. So let me pause this. Okay, so here we are with Desmos, and this is the function y is equal to x squared minus 2, and then the point is at 0, negative 1. Now, if I look at the x equals root 2 over 2, it's going to be somewhere around here, just right around there, okay? And it's at negative 3/2, which is what we are expecting. So you can imagine, this is going to be a little bit weird, but if I drew a line from 0, 1, the point that's in kind of the middle of the top of the screen, down to this location. So imagine I drew a line from here over to here, and then I swung that around in an arc and made a circle out of it. I would hit again at the location over here, but the distance would be less than if I went from here to here. And x equals 0 is the one that we have the extraneous solution for. So by just doing the checks that the 2 points of negative root 2 over 2 and positive root 2 over 2, that those were, the second derivatives were positive, which means that they were concave up, which meant they were minimums to the distance. So I know that's an awful lot to go over, but that's kind of the way that you do these problems. When you get your answers and you have more than one answer that's a solution, make sure that you kind of test and see if you have mins at those locations or if you have maxes. If you're trying to minimize something and you find that one of the points is a max, it's extraneous. Throw it out. And vice versa. If you're trying to find a max and one of your points winds up being a minimum when you do the second derivative test, throw it out. It's not actually a real solution. So there you have it. And now let's move to the next one. Okay. Let me go back. Okay, stop this and I'll go back to the actual blackboard. So here we go. Okay, so the next problem is quite a bit easier, and that was number 19. And for number 19, this is one of those problems that this one actually comes up in the real world. I've actually used this to build fencing to maximize area. So the problem is that you have some person wanting to build so this is water right here. It looks more like a road, but that's no water. They want to build a rectangular fence, and it gives you that the area that the fence has to encompass must be 405,000 square meters. Okay? It wants to know what is the minimum fencing needed to encompass an area of 405,000 square meters if one of the sides doesn't need fencing since it abuts a river. So we call this X and this Y, and we need to we need two things, right? We need a constraint and we need our min-max expression. So this is what is going to constrain it. And so how do we decipher, and that's the wrong word, how do we represent area in terms of this drawing? Well, that's just X times Y, right? So X times Y is equal to 405,000. And that is our constraint. We are constrained by that. So the next thing we need is our min-max expression. Well, the fencing that is going to build this consists of 2 Y's and 1 X. So I'm going to call that sort of a perimeter, even though it's not a full perimeter. So P is going to be X plus 2Y. Alrighty? This is my min-max expression. Okay, so now I need to solve for one of the variables in my constraint and plug it in order to constrain the min-max expression. So I'm going to solve for Y. Y is going to equal 405,000 over X. Okay, so I'm going to now take and plug in that constraint right there. So if I do that, I get P is equal to X plus 405,000 over X. Oh, and I don't want to forget that 2. So let me erase that a little bit. 2 times that. Well, that's going to be X plus, if you'll allow me, 810,000 X to the negative first. Well, why did I do that? It's because I'm going to have to take the derivative in just a second. It's better to go ahead and do that 1 over X as X to the negative first. So now I'm going to take the derivative. P prime is going to equal, well, the derivative of X is 1. and then it's going to be a minus sign because I've got a negative exponent here. So negative 1 times 810,000 is negative 810,000. And then x to the what? Negative second. Okay. Now that I've taken the derivative, I set it equal to 0. So p prime is equal to 0 gives us 1 minus 810,000 x to the negative second equal to 0. Okay. I'm going to rewrite that as 1 minus 810,000 over x squared equals 0. Come up here. That it means that 810,000 over x squared equals 1. I'm going to cross multiply. X squared equals 810,000. Okay? So I'm going to take the root of that. That means that x is equal to 900. Alrighty? So now that I've got x, I need y. Well, how do I figure out what y is? Well, y is 405,000 divided by x. So y is 405,000 divided by 900. And it turns out, drum roll, that's 450. So I'm going to have 450 feet of fencing for the y's and 900 feet of fencing for the x. Notice that if I add the y's together, it's 900. The x is 900. And yeah, that's, again, getting back to that whole strange values that are very similar to squares. We're not going to get into all that, but I now know what my x dimensions are, what my y dimensions are. So how much total fencing do I need to buy? Well, the total fencing is x plus 2y, so that's going to equal 900 plus 2 times 450, which is also 900. So I need to buy 1,800 meters of fencing. That is my final answer. That's the minimum fencing to encompass 405,000 square meters. And I really hope you enjoy that. That is absolutely stunning. That is so nice. If you ever find yourself building large enclosures for your pets, I highly recommend busting this out if you have a shared side or some strange configuration that like you're trying to divide it into maybe thirds. What's the optimal amount of fencing to get it? Use this. It is so nice. Just saying. I think you'd enjoy it. So there you go. That was optimization. And now we can move into anti-differentiation. So let's clear this and get going. Okay, so let's start off with a strange question. Okay, it's not that strange, but I haven't asked you this before. Let's say I have a function, f of x equals 3x squared. Now the question is, what function did I differentiate to give me 3x squared? So what function did I differentiate for this? Okay, so if you think about it for a little bit and kind of roll some values around, the answer is, drum roll, ready? Big F of x equals x cubed. Because when I differentiate x cubed, the 3 goes down in front, and then I subtract 1, right? Okay. Now, that's sort of the whole story, but what if I differentiated maybe x cubed plus 1. If I take the derivative of that, what do I get? Well, the derivative of that is 3x squared. Okay, what if I take the derivative of x cubed plus 2? Well, that's 3x squared. What if I take the derivative of x cubed plus 9,413? Well, it's still 3x squared. So my question is, which function did I differentiate to get this? Was it x cubed? Was it x cubed plus 1, x cubed plus 2, x cubed plus 9,413? The answer is it could have been any of them. And we have absolutely no way of telling. So a way to represent that uncertain value, notice that in every case, constant, 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 the constant disappears during the differentiation because it becomes a 0. So I'm now going to represent this as if my function was 3x squared, the function that I differentiated to get that was x cubed plus c. That c is a catch-all for a potential constant that disappears during the differentiation part because this is going to be a 0 when I differentiate it. Okay? So this right here is the general solution, because that c is a placeholder that stands for all the possible constants that could have been added to x cubed. Alrighty? Now, here we go. Just like there is a shorthand notation for saying what is the derivative of, that notation was with respect to x, right? ddx of something. There is a shorthand notation to say what function would I differentiate to get this function. Okay? So the notation for that we're going to be covering is the integral of f of x dx is equal to capital F of x plus c. Okay? And it doesn't matter. Your book uses uppercase c, uppercase, lowercase, same c's. It's fine. I've just do differential equations uses lowercase. I'm just used to using lowercase c's. But now what is this saying? This is right here, a couple of things. This is called the integral symbol. This right here is called the integrand. This right here is the with respect to. Oh boy, that just messed up. Let me try that again. With respect to. It's what you're differentiating with respect to, that you're anti-differentiating with respect to the variable. This right here is called the antiderivative. And this right here is our constant. But not just a constant, it has a special name. It's the constant of integration. And you're going to get sick of me saying constant of integration to you. Alrighty, so whew, that is an awful lot. What is this? Well, this is taking the integral of f of x with respect to x. So this thing right here is taking the integral of f of x with respect to x. Now, the other way to say that, to think about it, is you're finding the antiderivative of f of x with respect to x. Okay, so the antiderivative and the integral are interchangeable for the most part. There's a few little things that you have to be aware of, but for right now, they're pretty much the same thing. And all this is saying, what did I initially take the derivative of in order to get this f of x? So this is what I differentiated to get little f of x. And since the constant of integration would disappear when I differentiated, that's why it's a placeholder here. This can represent any of the constants that when I differentiated left me just f of x. Okay? So let's do a couple of examples, and I think it'll make a lot more sense. Well, I've just thrown a lot at you, and I know I have. So here we go. Let's say that f of x equals 2x. Okay? What was the function that I differentiated in order to get 2x? Exactly. X squared plus c. If I differentiate x squared, I get 2x. I differentiate c, I get 0. So the c encompasses all constants. So that's all I need. Alrighty. Now, if my f of x is, let's say 5, what function did I differentiate to get 5? Well, that function is 5x plus c. Okay, this is a weird way of thinking. You have to kind of, and I remember very, very well, first time I saw this, it really, really twisted my brain trying to think backwards like this. Okay, now we've done a few examples. Let's start making a table. So I'm going to clear this and we're going to make a nice table. All right, so the table is going to consist of f of x and capital F of x, which is going to represent what you differentiate to get f of x. Okay? So we have a few entries already. We had 3x squared came from differentiating x cubed. And if you'll allow me, I'm just going to not put the plus c in all these cases because I want to make a table that a pattern will pop out of. Alrighty. Now I had 2x came from x squared. 5 came from 5x. Okay? So I'm going to do a few more of these. What would I have to differentiate in order to just get x, plain old x? Well, I can do some scratch work. What is going to yield x if I differentiate? Well, If I differentiate x squared, I would get 2x, right? But I want x, so how do I get x if I differentiate x squared and get 2x? Well, 1/2 x squared will give me plain x. Let me actually write that out a little bit nicer where you can actually see it. So if I differentiate x squared, I wind up with 2x. How do I get x? Well, I'll multiply this by 1/2 and this by 1/2. I'd be left with 1/2 x squared equals x. Would you agree? If I just did some algebra. Well, differentiate 1/2 x squared. 2 times 1/2 is 1. And then I subtract 1 from the exponent. And I get x, which is exactly what I want. So what do I differentiate to give me x? I differentiate 1/2 x squared. Okay? Let me put some lines in here so that we're not too floaty. Okay? What if I had, maybe, what would I have to get if I had 5x? Well, if I know that if I differentiate x squared, and that gives me, let me go 4x. I really don't want to do an odd fraction. Change that to 4x. Okay, so that would be 2x. How do I get 4x? Well, I need to multiply by 2, multiply by 2. So what do I differentiate? Differentiate 2x squared. 2x squared. Sound good? Alrighty. So here we go. 5x. Well, a little more scratch work right here. I think I can squeeze it in actually. What do I differentiate? Well, if I differentiate x squared, I get 2x. But if I want 5x, I multiply by 5/2. 5/2. Does that hold? Absolutely. 2 times the 2 here will cancel, and it'll leave me with 5x. But I'll subtract 1 from the exponent. Okay, so here we go. We got a little table put out here. How do I go? Is there a pattern to go from my little f of x to the big f of x, which is what I differentiate to get the little f of x? Alrighty, well, I'm going to give you a big hint in that we already said that we're kind of having to think backwards, right? Instead of differentiating, we're thinking about what would I have differentiated? So if I take the derivative, so the derivative of x to the n, you remember, that's equal to n times x to the what? N minus 1. So the first step was I multiplied by n, then I subtracted from the exponent. Okay? Now let's look at this. Or any of these will work just fine. But we'll start up here. What did I do to go from 3x squared to just x cubed? Well, I can already see that in every single case, because this is times x to the 0, right? My exponent, this is to the first power. my exponents increase. They go up by 1. Okay? So, how do I go from 3x squared to x cubed? Well, I'm adding 1 to the exponent, but what happens to the 3? I need to get rid of it. Okay? I think we'll leave it like that for just a second. So I go from a 3 to basically a 1 right here. 3 to a 1. Now what about if I go from here to here? Well, I went from 2x to the first to 1x to the second. Okay, I'm going to jump all the way down here. 4x to the first becomes 2x squared. 5x to the first becomes 5/2 x squared. This one right here is the biggest clue of what's going on to go backwards. The only way I get 5/2 from 5 is if I divide by 2. And notice, that's the exponent. Let's see if that holds. If I look at the resultant exponent, which is a 3, and divide by that, this 3 divided by 3 becomes a 1. This 2 right here is my resulting exponent. If I divide the 2 by this 2, I get a 1. If I divide this 4 by this 2, I get a 2. So what's happening? Well, let me clear some space over here. It's just scratch work. The antiderivative rule is going to be, so the integral of x to the n dx is going to be x to the n plus 1 divided by that exponent. I'm going to look at the order. When I differentiated, I multiplied, so step 1 was multiply by the exponent, right? Step 2 was subtract from the exponent. Okay? If I want to go backwards, I need to not only change multiplication to division and subtraction to addition, I need to change the order. So instead of this one coming first, this piece has to come first. So I'm going to go backwards. So it's going to be, the first step is going to be add to the exponent. Second step is going to be divide by the exponent. Okay? That is the exact inverse of what I have here. And this is exactly what I have written down. I add 1 to the exponent, so get n plus 1, and then I divide by that amount. Divide by n plus 1. Looking over here, I have x squared will become x cubed, and then I'm going to divide by that. 3 divided by 3, 1. Right here, I add 1 to the exponent, so it becomes x squared, and then I divide by that, 5 divided by 2. And every one of these hold perfectly fine. Alrighty, so this right here is my antiderivative power rule. Okay, so let's clear this and do some examples with the power rule. Okay, so let's see. Let's do the integral of x to the fifth dx. Well, the power rule says I add 1 to the exponent, so x to the sixth, and then I divide by that exponent over 6 plus c. And that's exactly right. And I can always check it by differentiating. So if I differentiate my answer, x to the sixth over 6, do I get what I started with? Well, 6 times 1/6, which is what this would be, would become a 1. And then I subtract 1 from the exponent. What do you know? It's the same thing. Alrighty? So that is implying a very big truth, which we will get to in just a little. But for now, I just want to do some power rule problems. So let's do the integral of x to the fourth dx. Well, add 1, x to the fifth, divided by 5, plus c. Okay? Now for the big one, let's add this to it. What about the integral of 3x to the fourth dx? Well, this 3, since it is a constant, can move outside of the integral. This is the same as 3 times the integral of x to the fourth dx. Okay? Just like when we had the derivatives, we can move the constants. Because remember, if I had the derivative of 13x squared, that was the same as 13 times the derivative of x squared. Y'all remember that? This is 26x, we can just see looking at, but this would be 13 times 2x, which is still 26x. So you can always take constants across the derivative. You can also take constants across integrals, or the antiderivative. Okay? So what would this integral be? Well, that would be 3 times, add 1 to it, x to the fifth, divided by 5, which is going to wind up being 3/5 x to the fifth, or 3x to the fifth over 5. In other words, I don't have to move it on the outside. I could have just done 3x to the fourth dx. Well, I add 1 to the exponent, and I bring that constant with me, so 3x to the fifth divided by 5, plus c, plus c. And note they are exactly the same. So if I don't want to, I can move my constants. If I don't want to do the integral or the antiderivative with them inside of it, I can move them to the outside, do the integral on the variables, and then just make sure I multiply by the constants I took out. And that is absolutely 100% fine. Alrighty, let's do some more examples. So let's do the integral or antiderivative of, let's try 6x squared dx. Well, that's going to be 6x cubed over 3, and the 6 over 3 will reduce to 2x cubed. If I differentiate 2x cubed, do I get what I started with? Yep, because that would be 6x squared, which is exactly what I started with. So I know I did it right. This is the correct antiderivative or integral, and I always want to remember to do the plus c, because there might have been a constant in there. Alrighty, let's try something more complicated. The integral of x squared plus 3x dx. Okay, just like with derivatives, I can break an integral into multiple pieces. So I could have the integral of x squared dx plus the integral of 3x dx. I just broke it into two separate integrals. This would be add 1 and then divide by it. So x cubed over 3 plus add 1, divide by it, plus c. So that's that integral. Alrighty? Not too bad, hopefully. Alrighty, now, before I forget, I need to do something. We've already done it once, but I want to make sure that it's really sinking in. The integral of something like 5 dx. You add 1 to the exponent and then divide by it. There's not an exponent here, but it's hiding. This is x to the 0, right? Because x to the 0 is a 1, and 5 times 1 is 5, so that's what we have right there. So if I add 1 to it, that becomes 5 x to the first divided by 1, which is just 5x. So the integral of a constant is just that constant times x. And that makes perfect sense because if I take the derivative of 5x, I'm left with just a constant of 5. Sound good? Awesome. Now, I've been doing a ton of hand waving and saying that they're the inverses, blah, 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 but I'm going to very explicitly state that if I take, since they are inverses, they are the inverse of each other, I can do things like the integral of a derivative. They kind of cancel each other, and I'm left with just the plain old function. So the integral of a derivative is the function, because they cancel each other. It's kind of like the exponential of a natural log. They completely wipe each other out, like natural log of e to the x, it's just x, right? Or e to the natural log of x is x, because the natural log and the exponential wipe each other out. So same thing with the integral and the derivative. They completely negate each other, so I could also write it as the derivative of the integral of f of x dx is the original function. They cancel. Alrighty? So that is really nice. And this property right here is why I'm saying integral a lot, but you can always think of an integral as the inverse of the derivative, which we just kind of call the antiderivative. So this is the integral of 6x squared. It's also the antiderivative of 6x squared with respect to x. So you can call it integral, you can call it antiderivative. To be honest, you will never, ever, ever hear the word antiderivative said after this chapter. It will never come up again. It will always be integrals from that point on. Alrighty? So now that we've kind of said all of that, just want to hit 2 more things and then we are done. So here we go. So clear this. Now, if the integral is the inverse of the derivative, here's what we can do. The derivative of sine x is what? Cosine x. The derivative of cosine x is negative sine x, right? Now, here's your question. What is the integral of cosine x dx? Well, the integral of cosine x is what did I differentiate to get cosine x? And that is just sine x. Okay? So what is the integral of sine x dx? What did I have to differentiate to give me sine x? Well, I didn't differentiate cosine x to get sine x because it's a negative sign here. So what did I differentiate to get positive sine x? I differentiated negative cosine x. Now I probably need to put my plus c right there. Alrighty? So the trig functions are going to look like this. The derivative of tan x is secant squared x. The derivative of cotan x is negative cosecant squared x. The derivative of secant x is secant x tan x. And the derivative of cosecant x is negative cosecant x cotangent x. So the integral of secant squared x dx is tan x plus c. The integral of cosecant squared x dx is negative cotangent x plus c. The integral of secant x tan x dx is secant x plus c, and the integral or antiderivative of cosecant x cotangent x dx is negative cosecant x plus c. So notice I'm going backwards. The integral of this is what I have over here. But notice that I do not have, I have the integral of secant squared, integral of secant tan, all of that. I don't have a plain old integral of secant x dx. Turns out that is not easy. You actually can't figure out what that would be with the tools that we have right now. We're going to see how to do this when we hit chapter 5. So things to look forward to. Alrighty. Now, last thing. I know this is going long, but it is the very last thing, and it fits in really, really well. So let me clear this and go over it. Let's say that I have the integral of, or the antiderivative of 3x squared minus 1 dx. Okay? So how do I solve that? Well, I'm going to add 1 to the exponent and then divide by it. So this would be 3x cubed divided by 3 minus, what do I differentiate to give 1? Well, x. And then plus c. So this winds up being x cubed minus x plus c, right? Okay. Now, what if I told you that this expression, this solution right here, at x equals 2, my f, because these are the little f of x, the integrals or the antiderivatives are the capital F of x. So how do I could also say f of 2 equals 4. If you know what your antiderivative final value should be, when you plug in a certain value of x, you can then solve, because what I have here is this is my f of x equals x cubed minus x plus c. if I do f of 2, that's going to equal 2 cubed minus 2 plus c. But f of 2 is 4, so this is 4 equals 8 minus 2 plus c, right? So I've got, did I do that right? Minus 2 plus 2. Yeah, that looks right. I had to sit there and go, that looks strange. So now this is 4 equals 6 plus c. So I'm going to swing up here. C equals what? Negative 2. So now I can plug that in there, and I'm going to get x cubed minus x minus 2. Okay? This right here is what is called an initial condition. This is the kind of thing you'll have when you're running an actual experiment or looking at something in the real world. At a specific position, the result is this. If I plug that in to my equation that has a constant, just a placeholder, I can always solve for that constant and get this is the actual equation that governs this system. So, long story short, if you have an initial condition, you plug it into your expression, you turn the crank to solve for your C. Once you have solved for your C, you then plug that value into your general solution, and you have a specific. This is a specific or specific solution, or what's sometimes called a particular solution. But we're just going to say if you have an initial condition, you can always solve for the C when you integrate, and that lets you get the actual function. This right here is what I differentiated to get this with an initial condition. That's all I wanted to say. We will not be doing a lot of this, but you will certainly see it if you go all the way to differential equations. Oh my goodness. So, if you will, tackle for homework 15, 17, and this is from 4.1. We're in 4.1 now. 15, 17, 18, 20, 23, 27, and let's call that good. Let's start 18, 20, and 27. So those are the three I'll be going over at the beginning of next lecture. So good luck. I hope you enjoyed this. We are finally doing some of the really useful stuff that's about to pop out of this. You have no idea how useful this stuff is going to be. It's even more useful than the derivative in a lot of cases. So I hope you enjoyed it. Take care, stay safe, and I will see you next time. Bye-bye.